I'm standing in the heart of the Chilean desert, and towering behind me is one of the most extraordinary telescopes ever constructed on our planet. The Vera C. Rubin Observatory represents more than just advanced technology. It's $1 billion investment in humanity's quest to understand the cosmos. 2 decades of planning, engineering, and construction have culminated in this magnificent structure, housing the world's largest digital camera ever created. The capabilities of this telescope are almost beyond comprehension. It possesses such incredible sensitivity that it could detect the faint glow of a single lit candle resting on the lunar surface, nearly 240,000 miles away. I've traveled halfway across the world to Chile to understand the vision behind this remarkable achievement and to discover why astronomers are declaring it will revolutionize our understanding of the universe forever. Come with me as I take you behind the scenes of this incredible facility, where I reveal breathtaking science that has never been shared on YouTube before. My expedition to this remote Chilean desert observatory began thousands of miles away in Australia. After boarding my flight, I soared across the vast Pacific Ocean, and I knew I was approaching my destination when the majestic Andes mountain range came into view below. Following more than 26 grueling hours of travel, I finally touched down in La Serena, a charming coastal town that serves as home base for most of the scientists working at the observatory. The following morning, our team embarked on our ascent into the mountains. As we climbed higher and higher through the winding roads, the observatory gradually revealed itself on the horizon, an inspiring sight that made the long journey worthwhile. The telescope has been strategically positioned atop Cerro Pachón, a mountain peak rising from the otherworldly landscape of the Atacama Desert. The facility sits at an impressive elevation of 2,680 meters, that's approximately 8,800 feet above sea level. This remarkable height places the observatory well above the cloud layer, where the atmosphere remains exceptionally stable and clear, creating ideal conditions for astronomical observations. When I finally arrived at the summit and stood before this technological marvel, I was absolutely breathtaking. The scale and beauty of both the facility and its surroundings were overwhelming. This observatory represents literally 20 years of dedication and hard work. When the initial planning documents were being drafted, I was just a kid. It's hard to believe how much time has passed. But the dream began even earlier than that. Astronomers have been imagining this mission since the late 1990s, driven by an ambitious vision. Their goal was audacious: construct a specialized dark matter telescope capable of imaging the sky with unprecedented depth, breadth, and speed, 3 qualities that had never been combined in a single instrument before. The observatory bears the name of the brilliant astronomer Vera Rubin, who essentially discovered the existence of dark matter and devoted her entire career to studying this mysterious cosmic phenomenon. This distinction makes it the first United States national observatory to be named in honor of a woman, a fitting tribute to her groundbreaking contributions. Over the subsequent 2 decades, the mountaintop underwent a complete transformation. Construction crews built the massive observatory structure. Engineers carefully transported the enormous mirror up the steep mountain roads. And finally, technicians installed the largest digital camera ever manufactured, bringing the facility to completion. I was about to get an exclusive, behind-the-scenes look at this extraordinary achievement. And when I say exclusive, I mean truly exclusive. Later in this journey, I was granted a sneak preview of the very first images captured by the Rubin Observatory, and I'm thrilled to share them with you. The moment finally arrived when I was allowed to enter the observatory itself. I was escorted to the top floor of the facility, where both the massive telescope and its revolutionary camera reside. I wanted to witness firsthand how quickly this enormous instrument could reposition itself across the sky. Watching it move, I was genuinely impressed by the speed, especially considering that this telescope weighs as much as a commercial airliner. But here's the incredible part. What I was watching was a telescope operating at only 10% of its maximum capability. When they demonstrated the telescope moving at full speed, I could barely believe my eyes. Imagine taking a massive Boeing 747 aircraft, rotating it completely, and bringing it to a dead stop in approximately 4 seconds. That's essentially what this telescope can do. The entire moving assembly weighs 350 tons. Yet despite this enormous mass, the telescope is so precisely balanced and engineered that a single person can actually move it by hand. It's a triumph for mechanical engineering. This extraordinary speed is Rubin's true superpower, and here's exactly how it leverages that capability to transform astronomy. First, the telescope locks its focus onto a single enormous patch of the night sky, covering approximately 9.6 square degrees of celestial real estate. To put that in perspective, you could fit roughly 40 full moons side by side within that single frame. It's an incredibly vast area. Next, Rubin captures 2 consecutive exposures of that same patch. Each exposure leaves a camera's shutter open for 15 seconds, allowing the sensors to collect as much precious starlight as possible from distant celestial objects. Finally, within just seconds, the telescope rapidly shifts to the next patch of sky and begins the entire imaging sequence again, over and over throughout the night. It's this phenomenal speed that enables Rubin to capture approximately 1,000 high-quality images every single night of operation. That's enough imaging capacity to map the entire visible sky in just 3 nights of continuous observing, a feat that would have been unimaginable just a few years ago. Not everyone gets to experience what I'm about to describe. The true magic of this observatory flows from the LSSD camera, the largest digital camera ever constructed on Earth. This technological masterpiece is roughly the size of a compact car and weighs more than 3 tons. The imaging sensor nestled inside this beast of a camera can capture photographs with a resolution of 3,200 megapixels. For context, the images you take with your iPhone are probably somewhere around 40 megapixels. We're talking about 80 times more resolution. That massive sensor isn't a single piece. It's actually composed of 189 individual sensor chips that are meticulously arranged in a precise grid pattern to create the final composite image. The entire grid assembly is then cooled to negative 100 degrees Celsius to eliminate thermal noise that would otherwise degrade image quality. The result is an incredibly sharp, high-quality photograph of every single patch of sky that Rubin observes. Images of unprecedented clarity and detail. The sheer size of the patch of sky that Rubin images in a single frame is what truly sets it apart from every other telescope in existence. This is the coverage area of a single Rubin image, nearly 10 square degrees of sky. Here's a full moon shown to scale within that frame. Now, what about the famous James Webb Space Telescope? Well, each stunning JWST image you've seen, whether it's the pillars of creation, distant galaxies, or nebulae, is contained within this tiny fraction of what Rubin sees in one shot. While a telescope like JWST looks incredibly deep with astonishing detail at specific distant objects, Rubin uses its massive field of view to move rapidly across the sky and image the entire visible universe. The other remarkable feature of the LSSD camera is its ability to photograph each patch of sky through 6 different optical filters, and each one reveals something unique and beautiful about the cosmos. The ultraviolet filter illuminates hot, newborn stars that have just ignited their nuclear furnaces, along with brilliant supernova explosions. The blue-green filter shows us magnificent clouds of gas and dust that will eventually collapse under gravity to form the next generation of stars. The red filter highlights numerous bright stars scattered throughout the frame, along with asteroids silently drifting through our solar system. The I-band filter possesses the ability to peer through interstellar dust, revealing baby stars that have only recently been born within their cocoons of gas. The near-infrared filter functions like cosmic night vision, showing us cool red giant stars nearing the end of their lives, along with extremely distant galaxies whose light has been traveling for billions of years. And finally, the Y-band filter helps us cut through Milky Way's thick dust lanes to observe what's happening in the dense, mysterious core of our own galaxy. Scientists then combine the data from all of these filters to construct a complete, multi-wavelength view of everything happening in every patch of sky, a true cosmic rainbow. The final truly special piece of technology that I was privileged to see inside the observatory was the mirror system, or more accurately, the mirrors, plural. The telescope employs 3 large, precisely crafted mirrors that capture the incoming starlight and bounce it along a carefully designed optical path to focus it perfectly onto the telescope's camera sensor. The primary mirror measures 8.4 meters in diameter, while the secondary mirror spans nearly 4 meters across. The surface of this main mirror has been polished so incredibly smoothly that any imperfection across its entire surface measures less than 1/50th the width of a single human hair. To put this in perspective, if you scale this mirror to be the size of the entire United States of America, the tallest bump on its surface would still measure just a few millimeters tall. It's precision engineering at its absolute finest. Okay, so now we understand that the telescope moves with incredible speed to capture these enormous images of the sky using all kinds of sophisticated and expensive technology. So why invest all of that effort, time, and money to build something like this? What problems are they trying to solve? Well, there are 4 monumental scientific challenges they're tackling. The first objective is, naturally, to solve the profound mystery of dark matter and dark energy, the invisible substances that make up roughly 95% of our universe, yet remain almost completely unknown. By continuously imaging the entire visible night sky for 10 consecutive years, researchers are going to construct the largest, most detailed map of the universe ever created by humanity. By carefully analyzing the large-scale structure of the cosmic web, the filaments and voids that galaxies trace throughout space, they'll be able to map the distribution of dark matter throughout the universe, identifying where all of it is hiding. They'll use an effect called gravitational lensing, where dark matter's gravity subtly bends and distorts the light from extremely distant galaxies, creating telltale signatures that reveal the dark matter's location. Every telescope built before Rubin has collectively discovered around 5,000 Type Ia supernova events over the entire history of astronomy. Rubin is expected to discover hundreds of thousands of these crucial cosmic explosions every single year. These supernovae serve as standard candles that help scientists understand the nature and evolution of dark energy with unprecedented precision, potentially revolutionizing our understanding of why the universe's expansion is accelerating. Their second major goal is to comprehensively map the asteroids populating our solar system, finding as many as possible to protect our planet from potential impacts. This visualization shows the inner solar system right now, and all of these dots represent the catalog main belt asteroids that we currently know about. There are approximately 500,000 of them in our databases. Over the course of the 10-year survey, Rubin is projected to increase this number to over 5 million asteroids, discovering 10 times more than all previous observatories combined throughout history. And specifically, the telescope is hunting for the dangerous ones, asteroids that cross Earth's orbit and measure larger than 140 meters wide. Objects of this size are large enough to cause catastrophic regional damage if they struck our planet. Because the camera is so powerful and because they're imaging the sky so rapidly and repeatedly, they should be able to detect these asteroids months or even years before they might pose any threat to Earth. The telescope can spot them when they're still far away from our planet, rather than waiting for a close pass to detect them at the last minute, giving us precious time to respond. Their third goal is to spot transient events happening in real time that no other telescope in the world is currently capable of detecting at this scale. Remember, every patch of sky is imaged twice in quick succession, one exposure right after the other. This allows the newly captured image to be digitally subtracted from the previous image to search for any changes, no matter how subtle. Anything that has changed, anything new, anything that's moved, anything that's brightened or dimmed will be broadcast to astronomers worldwide as an automated alert within 60 seconds of detection. Look over there. A new asteroid has just been discovered. Oh, and over there, a massive star has just exploded in a spectacular supernova. And there's a tidal disruption event occurring, where a supermassive black hole is actively tearing apart and consuming a star. And it appears that this particular star is dimmed ever so slightly. Perhaps a planet is passing in front of it. And that's just 4 events I've mentioned. Here's the truly crazy part. Every single image Rubin captures will generate approximately 10,000 individual alerts. That's more than 10 million alerts being sent out per night of observation, an absolutely staggering flood of cosmic discoveries. And finally, their last major objective is to create a far better map of our own Milky Way galaxy than has ever existed before. Whenever you've seen images or animations of the Milky Way galaxy in documentaries or online, they have invariably been artist renderings or computer simulations. Of course, we haven't sent a camera probe outside of our galaxy to photograph it from above. That would take millions of years with current technology. So when you envision the Milky Way, you probably picture something like the beautiful spiral galaxy visualizations you've seen. But here's the reality. We have only actually observed and cataloged positions of around 3 billion individual stars within our galaxy. That represents less than 2% of all the stars the Milky Way contains. We're missing 98% of the picture. Rubin is going to provide us with a vastly improved map of the Milky Way, revealing the exact position, brightness, and color of over 20 billion new stars, 8 times more than any telescope has cataloged before it. This will transform our understanding of our galactic home structure, composition, and history. As the sun finally dipped below the horizon and set over the desert mountains, bathing the landscape in twilight colors, the observatory team began their preparations for a full night of astronomical observations. They captured a few test images to verify everything was functioning correctly and carefully calibrated the telescope systems before they started their scientific imaging program. I was even granted permission to remain up inside the massive dome of the telescope while they were actively imaging the universe, a rare privilege that few people ever experience. It was honestly one of the most special and moving moments of my entire life. As the luminous band of the Milky Way gradually rose above the observatory dome, painting the sky with countless stars, I couldn't quite process what my eyes were seeing. It was unquestionably the clearest, most beautiful night sky I had ever witnessed in my life. The absence of light pollution at this remote location made the stars appear almost three-dimensional, as if I could reach out and touch them. We eventually headed back down to the control room, where I was about to be shown something extraordinary, the first ever scientific images captured by the Vera Rubin Observatory. And honestly, they were absolutely magical. They exceeded even my highest expectations. And now I can finally share them with you. Are you ready? What you're looking at here is the very first image ever taken by Vera Rubin. Isn't it absolutely stunning? But watch this carefully. We can zoom out further and further and further still, revealing more and more detail, until we finally get a complete view of the entire image at full resolution. All of that incredible detail. Every star, every galaxy, every wisp of cosmic gas is captured in a single Rubin observatory frame. Each corner of the image tells a different story about our universe. Galaxy mergers occurring billions of light years away. Distant galaxies from the farthest reaches of our observable universe, their light having traveled for eons to reach us. Brilliant stars in various stages of their life cycles. Vast clouds of gas and dust where new stars are being born at this very moment. It's genuinely, breathtakingly beautiful, a masterpiece created not by human hands, but by the cosmos itself and revealed through human ingenuity. And all of this cosmic wonder is contained within a single frame, captured in just 30 seconds of total exposure time. Now imagine what Rubin will discover by taking images like this every single night, non-stop, for 10 full years. The potential for discovery is almost limitless. Everything in astronomy really is about to change. But here's what really excites scientists about this observatory. Beyond all the known science goals I've described, there are the truly rare events, the 1 in a billion occurrences, or even more rare than that. We will start finding those events that we didn't even know existed. The most thrilling thing about this observatory, according to the scientists I spoke with, are these so-called unknown unknowns that it will inevitably discover. These are the amazing discoveries that we aren't even thinking about or predicting right now. Phenomena that will simply jump straight out of the data, completely surprising us and potentially changing the entire course of science forever. We've witnessed this pattern time and time again throughout the history of astronomy and space exploration. Voyager 1 discovered active volcanoes on Jupiter's moon Io, something nobody had predicted. The Hubble Space Telescope helped astronomers conclude that the universe's expansion is actually accelerating, not slowing down, a discovery that earned a Nobel Prize and completely transformed cosmology. The list of serendipitous discoveries goes on and on. We simply don't know what amazing discoveries might emerge from these unprecedented images of the universe. Perhaps we'll discover a new type of cosmic phenomenon that doesn't fit into any existing category. Perhaps we'll find evidence that forces us to rewrite our understanding of gravity or cosmology. Perhaps we'll spot something so unexpected that it opens entirely new fields of research. And to me, there's absolutely nothing more exciting in science than those eureka moments of blind discovery, when something completely unexpected reveals itself and forces us to question everything we thought we knew. And I'd be willing to bet everything I own that this telescope, This remarkable achievement of human curiosity, engineering, and determination will bring us plenty of those mind-blowing, paradigm-shifting moments in the years to come. The universe is vast, ancient, and full of mysteries. The Vera C. Rubin Observatory is humanity's newest and most powerful tool for unveiling those mysteries. But my journey wasn't quite over yet. The most incredible moment was still to come. As I stood in the control room, watching the scientists analyze the first images streaming in from the telescope, something extraordinary happened. One of the astronomers suddenly leaned forward, her eyes widening as she stared at her monitor. "Wait! What is that?" she whispered. The room fell silent. Everyone gathered around her screen, and I could feel the tension building. On the monitor was an image from one of Rubin's test observations, a patch of sky that had been photographed just hours before. "That wasn't there in the previous surveyed data," another scientist said, his voice barely containing his excitement. That's completely new." They were looking at something that appeared to be moving, a faint streak of light that hadn't been visible in any previous observations of that region. But it wasn't an asteroid. It was moving too slowly, and it wasn't behaving like anything they'd seen before. Within minutes, the control room erupted into control chaos. Scientists were pulling up comparison images, running calculations, making urgent phone calls to astronomers at other observatories around the world. I stood there, forgotten in the corner, watching this real-time scientific discovery unfold before my eyes. "We need follow-up observations immediately," the lead astronomer announced. "Can we retard the telescope?" "We're on it," came the reply from the telescope operator. This was it. This was a moment that all those years of planning, all that investment, all those sleepless nights were building toward. The telescope that could respond faster than any other in the world was about to prove its worth. The massive dome rotated smoothly. The telescope repositioned itself with breathtaking speed. And within minutes, Rubin was locked onto mysterious object again. The room held its collective breath as the new images appeared on screen. The object was still there, but now it was clearer, much clearer, and stranger. "It's not reflecting light like a typical celestial body," one scientist muttered, studying the spectroscopic data. "The wavelengths are unusual." "How fast is it moving?" someone asked. "That's the thing," came the response. "It's accelerating. Objects in space don't just accelerate on their own unless something is pushing them." My heart was racing. I'd come here to document a new telescope, but I was witnessing something far more profound. I was watching astronomers discover something that didn't fit into our current understanding of the cosmos. They continued observing throughout the night, each new image revealing more puzzles. The object trajectory didn't match any known orbit. Its spectrum showed elements and combinations they'd never seen before. And most intriguingly, it appeared to be changing, evolving as they watched. As dawn began to paint the eastern sky with pale light, the lead astronomer finally stepped back from the monitors and addressed the room. "Ladies and gentlemen," she said, her voice trembling slightly with emotion, "in less than 24 hours of operation, the Vera C. Rubin Observatory has detected something that might challenge our understanding of physics. This is exactly why we built this telescope. This is what discovery looks like." The room erupted in applause, but there was also an undercurrent of uncertainty. The good kind, the kind that drives science forward. They didn't know what they'd found yet. It would take weeks, maybe months of additional observations and analysis to understand what this object really was. But that's the beauty of astronomy. That's the magic of building something like Rubin. As I descended the mountain the next morning, exhausted but exhilarated, I couldn't stop thinking about what I'd witnessed. I'd arrived hoping to understand why they built this telescope. I'd left having seen it prove its worth in the most spectacular way possible. The scientists had asked me not to reveal the details of the discovery. Not yet, not until they'd had time to verify and analyze their findings properly. Science moves carefully, deliberately, even when discoveries are exciting. But they promised to keep me updated, to let me know what they eventually figured out about that mysterious object. Looking back now, I understand something profound. The Vera C. Rubin Observatory isn't just about answering the questions we already have about dark matter, dark energy, asteroids, and the structure of our galaxy, though it will revolutionize all those fields. It's about being ready for the questions we haven't thought to ask yet. It's about building a tool so powerful, so fast, so comprehensive, that it can catch the universe in the act of showing us something completely unexpected. That night in the Chilean desert, I watched a billion-dollar investment justify itself in real time. I watched 20 years of planning and construction pay off in a single moment of discovery. I watched the future of astronomy begin. And here's what keeps me up at night in the best possible way. That object we discovered, whatever it turns out to be, was found in just the first few hours of test observations. The telescope hasn't even begun its official 10-year survey yet. Think about that for a moment. In 10 years of continuous observations, capturing thousands of images every single night, monitoring billions of stars and galaxies, tracking millions of asteroids, and generating 10 million alerts each night, how many more mysteries will Rubin uncover? How many more objects that shouldn't exist will it find? How many more phenomena that challenge our textbooks will appear in its images? How many more times will astronomers gather around a monitor, pointing at something on screen and whisper, "Wait, what is that?" The unknowns aren't theoretical anymore. I've seen one with my own eyes. I've watched scientists scramble to understand something that appeared in their data, without warning, without precedent, without any existing theory to explain it. Standing in that control room, watching history unfold in real time, I finally understood why everyone said this telescope would change astronomy forever. It's not just about making better maps or finding more asteroids or capturing prettier pictures, though it will do all those things magnificently. It's about expanding the boundaries of human knowledge into territories we didn't even know existed. It's about being surprised by the universe. It's about maintaining our sense of wonder in the face of cosmic mysteries that are larger and stranger than we ever imagined. The Vera C. Rubin Observatory represents humanity at its best. Curious, ambitious, persistent, and brave enough to ask questions when we know the answers might change everything. As my plane lifted off from Chile, carrying me back home across the Pacific, I looked out the window at the Andes Mountains disappearing behind me. Somewhere up there, on top of Cerro Pachon, a telescope was continuing its work, scanning the sky, taking pictures, searching for anomalies, waiting for the next surprise. And I smiled because I knew with absolute certainty that there would be more surprises. Many more. Some might even rival what I'd witnessed that incredible night. The age of discovery hasn't just begun, it's accelerating. And thanks to the Vera C. Rubin Observatory, we're finally ready for it. The universe is vast, ancient, and full of mysteries. But now, for the first time in history, we have a telescope powerful enough, fast enough, and smart enough to catch those mysteries in the act of revealing themselves. And I got to be there on that mountaintop in Chile when it all began. That's a story I'll be telling for the rest of my life. But this story doesn't end there. 3 weeks after I returned home, I received an encrypted email from Dr. Sarah Chun, the lead astronomer I'd met at the observatory. My hands trembled slightly as I opened it. "You're not going to believe this," the email began. "We've been tracking that object continuously since you left. We've coordinated with 12 other observatories around the world. And we finally have answers, or at least more questions that are even more interesting." She'd attached a secure video call link and asked if I could join a conference in 2 hours. I immediately cleared my schedule. When the video call connected, I found myself staring at a grid of faces, astronomers from MIT, Caltech, YESO, and institutions I'd never even heard of. Dr. Chen's face appeared in the center square. "Thank you for joining us," she said. "We wanted you to hear this first, because you were there when we made the initial detection. What we're about to share with you will be published in Nature next week, but we thought you deserved to know now." My heart was pounding. Around me, other scientists were logging in. I counted at least 40 faces on the screen now. "The object we detected," Dr. Chen continued, pulling up a series of images on a shared screen, "is unlike anything in our catalogs. After 3 weeks of intensive observation and analysis, we've determined that it's not a comet, not an asteroid, and not any known type of natural celestial body." The room, or rather, the virtual room, was completely silent. Its acceleration pattern suggests it's under some form of propulsion. The spectroscopic signature shows materials that shouldn't exist together in nature. And here's the most intriguing part. She paused, and I could see her choosing her words carefully. It's emitting a structured signal. Someone unmuted their microphone. Structured how? Dr. Chin pulled up another screen, this one showing a waveform pattern that pulsed in regular intervals. It's repeating every 7.3 hours. The pattern isn't random. It follows a mathematical sequence. We've had our best cryptographers and mathematicians analyzing it. Are you saying... I started, then stopped, almost afraid to finish the sentence. We're saying this is techno-signature detection. Another scientist chimed in. This is what we've been searching for since we started SETI 70 years ago, and it appeared in Rubin's first operational night. The implications hit me like a physical force. The telescope designed to find asteroids and dark matter had potentially discovered the first confirmed evidence of technology from beyond Earth. Over the next few days, the story began to leak despite everyone's best efforts to keep it contained. Conspiracy theories exploded online. Government agencies started asking questions. And the Rubin Observatory became the center of the most intense scientific investigation in modern history. I flew back to Chile. I had to. This was no longer just a story about a telescope. This was potentially the most important discovery in human history, and it had happened right in front of me. When I arrived at the observatory this time, the atmosphere was completely different. Armed security guards checked credentials at multiple checkpoints. Satellite trucks from news organizations around the world were parked at the base of the mountain, denied access to the summit. The normally quiet facility was buzzing with activity. Dr. Chin met me at the entrance, looking exhausted but energized. It gets stranger, she said without preamble. The object is responding to our observations. What do you mean, responding? Every time we point Rubin at it, the signal changes. Slightly, but measurably. It's like... She paused, searching for the right words. It's like it knows we're watching. The control room had been transformed into something resembling NASA's mission control. Scientists worked at dozens of stations, each monitoring different aspects of the object. Screens displayed real-time data feeds from telescopes around the world, all coordinated to study this single mysterious visitor. We've named it Envoy 1, Dr. Chin told me, because if our hypothesis is correct, that's exactly what it might be, an envoy, a probe sent to explore, just like we sent Voyager. On the main screen, I could see the object, now rendered in much higher detail thanks to weeks of continuous observation. It was roughly cylindrical, about 400 meters long, with a surface that seemed to shift and shimmer in ways that defied normal physics. How far away is it? I asked. That's the concerning part, replied Dr. Martinez, another senior astronomer. It's decelerating. When we first spotted it, it was beyond Neptune's orbit. Now it's crossing Saturn's orbit. At its current trajectory and deceleration rate, he pulled up a projection on screen. It will reach Earth's orbital path in approximately 18 months. The room fell silent again. Everyone knew what that meant. 3 days into my second visit, at 2:47 a.m. local time, a young graduate student named James Chun, no relation to Dr. Sarah Chun, let out a shout that woke up everyone in the facility who'd been trying to sleep. I've got it. I've decoded part of the signal. Everyone rushed to his station. On his screen was a visualization of the signal pattern, but now it was overlaid with translations, mathematical concepts rendered in universal constants, prime numbers, the ratio of a circle's circumference to its diameter, the fine structure constant. It's a primer, James explained, his words tumbling over each other in excitement, like the plaques we put on Voyager. They're teaching us their language using mathematics, concepts that will be the same anywhere in the universe. Over the next 72 hours, working around the clock with linguists, mathematicians, and cryptographers from around the world, they began to unravel more of the message. And what they found was both beautiful and haunting. The message contained star charts, maps of our galaxy from a perspective far from Earth, chemical formulas for organic molecules, diagrams that appeared to show biological structures. And then, the part that made everyone stop and stare, images. They were highly compressed, encoded in the signal itself. The first image showed a world, not Earth, but another planet with continents and oceans under an orange-tinted sky. The second showed structures, cities, maybe, or something that served a similar purpose. The third showed beings. They were nothing like us. Tall, almost crystalline in appearance, with geometries that hurt to look at for too long. But they were undeniably intelligent, undeniably real, and undeniably reaching out across the vast emptiness of space to say, "We are here. You are not alone." Dr. Chin made a decision that will be debated by historians for centuries to come. After consulting with a hastily assembled international committee, they decided to respond. Using the Rubin Observatory's capability to modulate its imaging systems, they crafted a return message: more prime numbers, more mathematical constants, and images of Earth, our blue marble hanging in space, our cities, our people, our diversity. At exactly midnight Chilean time, they transmitted, and then they waited. The object was still millions of kilometers away. Even at the speed of light, the message would take hours to reach it, and hours more for any response to return. The control room settled into an anxious vigil. I sat in a corner, my camera forgotten for once, just watching these scientists who had suddenly become humanity's first ambassadors to an alien civilization. The weight of the moment was crushing and exhilarating in equal measure. At 7:14 a.m., as the sun rose over the Atacama Desert, painting the sky in shades of pink and gold, the signal changed. It wasn't just a continuation of the previous pattern. It was new. It was acknowledgement. It was, in the most profound sense possible, a conversation. I'm writing this now, 6 months after that historic transmission, and the world has changed in ways I'm still trying to comprehend. Envoy 1 continues its approach, still 18 months from reaching Earth's vicinity. The message exchange continues, with each transmission revealing more about this other civilization and teaching us profound lessons about our place in the cosmos. The Rubin Observatory has become more than just a telescope. It's become humanity's window to our cosmic neighbors. And while dozens of other observatories now monitor Envoy 1, it was Rubin that found it first. It was Rubin that was fast enough to catch it. It was Rubin that made first contact possible. Dr. Vera Rubin spent her life proving that there was more to the universe than we could see. Hidden matter, dark and mysterious, making up most of reality. How fitting that the telescope bearing her name would reveal something even more profound. That hidden among the darkness and the vast distances, there are others looking up at the stars, just like us. When I first visited the observatory, scientists told me about unknown unknowns, discoveries they couldn't even imagine that would jump out of the data. They were thinking about new types of stars, unusual galaxies, bizarre cosmic phenomena. None of them, not one, predicted this. That's the thing about genuine discovery. It doesn't just answer our questions. It shows us we were asking the wrong questions all along. We built Rubin to find dark matter and asteroids. It found intelligence among the stars. What else is out there, waiting to be discovered? What other revelations will emerge from Rubin's decade-long survey? If the first month brought us this, what will 10 years bring? I don't know. Nobody knows. That's what makes it beautiful. My journey to the Chilean desert started as a simple mission to document an impressive telescope. It became something I could never have imagined, a front-row seat to humanity's first confirmed contact with extraterrestrial intelligence. The Rubin Observatory sits on that mountaintop still, scanning the sky every clear night, taking thousands of images, generating millions of alerts. But now we understand its true purpose. It's not just looking for answers. It's looking for questions we haven't thought to ask yet. It's listening for voices we didn't know were calling. It's watching for wonders we couldn't have dreamed existed. And somewhere out there, millions of kilometers away, but drawing closer each day, Envoy 1 continues its journey toward our small blue world. Its message continues to unfold, each new transmission teaching us more about the vast and populated universe we inhabit. I still get emails from Dr. Chin regularly. The latest one arrived this morning. You should come back. There's something new in the data. Something from a different direction this time. Rubin found another one. Another one. The universe isn't just vast, ancient, and full of mysteries. It's full of life, full of intelligence, full of civilizations looking up at their skies, just as we look up at ours, wondering if anyone is out there. And now we know the answer. Yes, we are here. They are there. And thanks to a billion-dollar telescope on a mountaintop in Chile, we're finally beginning a conversation that might define the next chapter of human civilization. The age of discovery hasn't just begun. It's exploded into something far more magnificent than we ever imagined. And I was there, on that mountain, on that night, when everything changed. This is the story of the Vera-C Rubin Observatory. This is the story of first contact. This is the story of how we learned we were never alone. And the truly incredible part? This is just the beginning.